The view that you see behind me is, I think, my favorite view of Saturn. It's a view that was taken... Oh, it wasn't that view. That's my favorite view of Saturn. I jumped in too quickly, I'm sorry. The reason I love it so much is it was taken by the Cassini spacecraft over quite a long period of time. So it consists of lots of different images that the camera on board Cassini took. And it effectively shows you a view of the Saturn system, of the planet itself, of the visible rings that we've all seen for quite a long time through telescopes and images from other spacecraft. But also you can see a new ring called the E ring, which is a rather diffuse ring. And within that ring, those of you with good eyesight can see that there is a moon inside of that ring. And those of you with really good eyesight will see that that moon seems to appear lots of different times, and the reason for that is it's more than one image, so it's images over a period of time which have been put together. And what you can also see is there's this plume which seems to be coming out of the ring, and that's one of the things I'm going to talk to you about this evening. And that's a discovery that my team made of a water vapor plume from the small moon called Enceladus, which is the moon you can see in that ring, and which actually forms that diffuse E-ring that you can see. And the other reason that I love that image is you can see the Earth in the image. And I'm not going to turn around often to point because it's really difficult to point on this one, but let me just show you where it is. There's the Earth there. And so every time I look at that, the hair on my arm stands up on end because it's really strange to be seeing us from such a far from such a far distance away. So what I'm going to talk to you about tonight is the science and the discoveries that we made with the Cassini spacecraft at Saturn. But before I do that, I just want to give you a little bit of history and remind you that to begin with, we really didn't understand Saturn at all. These are some hand-drawn images that were made of Saturn. Well, first of all, Saturn was discovered by Galileo in 1610. But he really didn't understand what he was seeing. When he looked at Saturn through one of the first telescopes, it looked as if to begin with it had a moon on either side. And then sometime later, it looked as if that moon, those moons had almost merged into what looked like rings. And you can see the different pictures that were put together over time. And it was only in 1655 when Christian-Huygens and the European Space Agency probe that was on the Cassini spacecraft was named after Christian-Huygens. He realized that what we were actually seeing was this set of rings. And the reason that you weren't seeing them all the time is that depending on the changing seasons, the orientation of the rings changes. And so if the rings are flat on to the Earth, you can't actually see them, whereas if they're at an angle, you can see them much more clearly. And this is actually the 1655 sketch that Huygens made of Saturn, and he was the first scientist to propose that it was actually a solid ring that we were seeing. And then Cassini discovered some of the moons after that. But in fact, it's not a solid ring. It consists of countless individual particles, each in their own orbit around Saturn, but because they're so dense, the ring looks pretty solid. And you'll see some images of some close-ups of the rings later. So moving on to the Cassini mission itself, it was originally called the Cassini-Huygens spacecraft because there was the European Space Agency Huygens probe, which detached from Cassini and traveled down through the atmosphere of Titan. But in this view here, you see what a large international mission it was. That shows you the flags of all the different countries of the scientists and engineers who were involved. The people in my team were based in the UK, in the States, in Hungary, and in Germany. And the instrument that I was responsible for was on that long boom that you can see, covered in gold foil. Most of the spacecraft was covered in gold foil. And that was to keep the instruments and the spacecraft at a temperature where they could actually work out in space, because it gets rather cold out at Saturn. The reason that we put the instrument, which is the magnetometer, which measures the magnetic field in the vicinity of the spacecraft, the reason it's always put on this long boom is what we're trying to do is measure the magnetic field due to the environment and not due to the spacecraft itself. So we try and get it as far away from the spacecraft as we can. And in a couple of slides' time, I'm going to show you some images of the two instruments that made up the instrument suite. The one which was built at Imperial College was halfway down the boom, so at 6.5 meters. and the one that was built at the Jet Propulsion Lab was right on the end of the boom. The white umbrella-shaped thing that you can see, that was known as the high-gain antenna. And when we were in orbit around Saturn, once a day, what would happen is the high-gain antenna would point back at the Earth and would send data back down to the Earth from the previous 24 hours. This view here shows you the Cassini spacecraft in its test chamber before launch. One of the reasons I like to show this is it shows you how big it was. You can see a person standing down at the bottom. And you can also see that the magnetometer boom, where my instrument was placed, isn't there. In fact, it is there. It's in that little canister that you can see on the side, because if you think about it, you can't launch a spacecraft with a large boom sticking out from the side. And so what we did is after launch, we actually deployed the boom so that we could start taking the data that we wanted to take. One of the reasons the spacecraft was put into this large test chamber was so that we could test that the instruments and the spacecraft could operate in vacuum, which is what they needed to do out in space, but also that they could survive the different type of temperatures that they would have to operate in outer space. I'll show you a spacecraft trajectory, so the way in which we got out to Saturn, but we used flybys past some of the other planets in the solar system to give us a kick to get us out to Saturn. And so we went to Venus, where it's about 40 degrees Celsius, and then once we got out to Saturn, it was about minus 170 degrees. And so the instruments really needed to operate in quite a wide operating range. So this here is the is photographs of the two instruments that consisted of the MAG suite. The one in the top left is the Fluxgate magnetometer, and that's what was built at Imperial College in London. And we've still actually got the flight spare instrument. And when the instrument was still operating in orbit around Saturn, what we used to do is before we sent commands to the instrument, we would test them on the flight spare that we had to make sure that they did what we wanted them to do. Because it takes 40 minutes, or it took 40 minutes for a command to get out to the spacecraft, and then another 40 minutes for us to find out whether it worked or not. And so we needed to be sure that we actually did it well, that we sent the right commands. The one on the bottom right was the vector helium scalar sensor. That was built at the Jet Propulsion Lab in California. That was the one at the end of the boom. One of the reasons that we always try and fly two instruments is because the zero level of the instrument changes over time. And the kind of science that we want to do, we need to know where the zero of the instrument is. And so we use the two instruments to almost calibrate each other and make sure that we understand what the actual calibration is. A complication for us is a year after we got into orbit around Saturn, the instrument at the end of the boom stopped working. And so what we had to do is we had to do a very complicated calibration procedure where we had to roll the entire spacecraft in two separate directions so that we could work out what the zero of the instrument was. And that was rather difficult to do, and it also impacted some of the other instrument science as well. So you can't talk about a spacecraft mission unless you show a slide that shows launch. And so this was the launch in 1997 on the 15th of October from Kennedy Space Center. I was about 10 miles away, I think. It was the first launch that I ever went to. And what really hit me was the fact that you saw it taking off, and as the sound hit you, the ground began to shake. And I actually had a colleague that was with me, and she was using a video camera to video the launch. And she didn't realize that the ground was going to shake either. And so the video is actually jumping up and down. And we watched it once or twice, but we got a bit seasick after that. And so we didn't actually use that again. So as I mentioned a little earlier, particularly when we need to get into the outer solar system, we usually fly past other planets to gain a gravity assist so that we can actually do that. Because particularly with the spacecraft launches that we've used in the past, they don't have enough power to get a spacecraft as large as Cassini with enough fuel on board to get us straight out to Saturn. And so what this view shows you here we're looking down on the equatorial plane of the solar system. You have the sun right in the center, and then you can see the orbits of the different planets marked, and you can see the trajectory of the spacecraft as well. And so the launch took place, as I said, on the 15th of October, 1997. We flew past Venus twice, and the reason that we fly past other planets, it's a little bit like if you've got a stationary billiard ball and a moving one, if the moving one bumps into the stationary one, it gives it a little bit of a kick and a little bit of energy and it gets it moving. And that's essentially what we do as far as planetary flybys are concerned. We get the spacecraft close enough to the gravitational pull of the planet to allow it to gain a little bit of extra energy, and that then pushes us out, speeds us up and gets us out to the next planet that we're planning to fly by. So we flew past Venus twice, we flew past the Earth once, and we actually used that Earth flyby to calibrate our instrument. Prior to the Earth flyby, we deployed the boom, and we made measurements as we flew past the Earth, because we understand the magnetic field of the Earth pretty well, and so we wanted to calibrate our instrument on that flyby to make sure that we understood the data that we were getting. We then had a flyby past Jupiter, and then we finally reached Saturn in July 2004. And so it took us 6.5 years to get there. So you need lots of patience to be involved in outer planetary missions. I'm involved in the Jupiter mission called JUICE, which is going to be launched in 2022, and it will get to Jupiter in 2030. I won't tell you how old I'll be, but I've made sure I've got lots of young scientists on the team so that whatever age I am, they'll be there to help out as well. So these were the 4 main science targets of the Cassini spacecraft. I'm not going to have time to talk about all of them. I'm going to focus on 2 of them. But just for completeness, let me just go through them. So top left, we've got Saturn and its rings. One of the things that we still don't understand, and it's a little bit embarrassing to say that, is we don't really know how long a day on Saturn is. We think it's about 10.5 hours, but it could be 10.6 hours, it could be 10.7 hours. And the reason we don't know how long it is, if you think about it, is the surface is not solid, it's a gas giant. And so you can't watch a feature on the surface go around and see how long it takes to go around. You also can't do that at Jupiter, but at Jupiter, the magnetic field, the rotation axis of the planet and the magnetic axis has a tilt between them. And that allows you to work out by watching as the planet rotates on its axes how long a day is. On Saturn, the axes seem to lie on top of each other. And so that's one of the reasons why we haven't been able to find out what the length of the day is. And the fact that they lie on top of each other is a real surprise. This is not something that was expected at all, and we're still trying to understand that. In the top right, we have Titan. Titan is the largest moon of Saturn, and it's the only moon in the solar system that has a very dense atmosphere, very similar to what the Earth's atmosphere used to be like when it first formed. And so Titan was a real focus of the Cassini mission. So Cassini, with all the mission extensions that we had, I think it flew past Titan in total about 129 times. But in addition to that, the European Huygens probe traveled down through the atmosphere of Titan. It made measurements in the atmosphere, and then it made measurements on the surface as well. And one of the reasons we were so keen to do that is it almost gives us insight into how the Earth's atmosphere has evolved over time. Bottom left is an image from from the Voyager spacecraft, actually, of one of the icy moons of Saturn. That's actually Enceladus, and that's one of the moons I'm going to talk to you about later. And one of the things about Saturn is that lots and lots of moons. Every time you look, there are more. I think the latest number was 63, but there's some extra ones within the rings as well, which don't really count as separate moons. They're sort of moonlets that orbit with the rings and change the shape of the rings. And then last but not least, on the bottom right is the region around Saturn, which is protected by the magnetic field of Saturn, and that's known as the magnetosphere. We have a similar region around the Earth as well. What happens is the magnetic field of the Earth protects us from the effects of the solar wind and the sun and the energetic particles coming from the sun. And we have the same thing happening at Saturn. And by spending a lot of time in an environment, you can best understand all the different processes that are taking place inside. But I'm not going to talk in any detail at all about either Titan or the magnetosphere. I'm now going to focus on looking at some of the data that we got from Enceladus. But before I do that, I just wanted to tell you a little bit about what the instrument actually measured. And so we measure them, well, I keep saying we measure. We used to measure the magnetic field at Saturn. And what we do is the magnetic field is a vector. So before I talk about the vectors. The view that you can see there shows the Earth. On the Earth, we have a magnetic field which is generated in the interior by planetary dynamo action. What we think happens is there's an overturning, bubbling motion as heat is given off. There's a rotation and a convection taking place in the interior, and there's a current that flows. And that current generates the magnetic field that we can see outside. Now, you can't actually see field lines, but what you can do is measure them. And if you could see them, they would look like those red lines that you can see there. And so that's what my instrument measured, is it would measure the magnetic field lines outside of Saturn, which actually allows you to get a better understanding about what goes on inside. But the other thing I'm going to want you to keep in mind as you look at the data is that as Saturn rotates on its axis once every about 10.5 hours, those field lines are going to be moving at the same rate. And so if you watch an individual field line, it's going to take 10.5 hours to rotate as Saturn does. And that's something that I'm going to ask you to keep in mind when I show you some of the slides that follow on. And the way in which we measure the magnetic field is it's got a direction and it's got a strength. And so we measure it in 3 different components, and you then add those together to work out what the actual magnitude or strength of the field is. Okay, so this is Enceladus. This is a view which was taken by the camera on board Cassini as we approached Enceladus in 2005. And one of the first things that will strike you is how young the surface looks. There are hardly any craters on the surface at all. And this was a real surprise, and it was very different to one of the moons close by. I'll come back to this slide in a second, but just to orient you as to where Enceladus is as far as its orbit around Saturn. So what you can clearly see there is Saturn itself. You can see the visible rings, and then you can see where the different moons in orbit around Saturn are. Enceladus is lying in the middle of the diffuse E-ring, and the moon just inside of Enceladus, which is called Mimas, its surface is covered in lots and lots of different craters. And so the fact that Enceladus doesn't seem to have many craters on its surface seemed to imply that there was something going on at Enceladus, something that was resurfacing it, something that was making its surface younger than the surfaces of the moons close by. The other thing that we had in the back of our minds about Enceladus was that it had long been thought that somehow Enceladus was the source of this E-ring, partly because the surface of Enceladus we knew was made up mainly of water ice. We found that out when the Voyager spacecraft flew past Enceladus in the late 70s. And we knew that the material in the E-ring seemed to be water ice. So there was a question about whether it was a source of the E-ring. There was the surprise that the surface was as young as it was. But there were also these cracks on the surface as well. And so we had this in the back of our minds when we had our first flyby of Enceladus. And this took place in February 2005, so about 8 months after we went into orbit around Saturn. And the first flyby was quite far away. You can see the distance on the slide there. It was 1,265 kilometers above the surface. Now, Enceladus is quite small. It's got a diameter of about 500 kilometers, so we were quite far away. And then a month later, there was a second flyby, which was 500 kilometers away. And based on the data that the magnetometer instrument measured on those first 2 flybys and our understanding of what we thought we were seeing, we actually persuaded the Cassini project to take us much closer on the third flyby. So originally, the third flyby, which took place in July 2005, was supposed to be 1,000 kilometers away. But based on what we thought we were seeing, we persuaded them to take us really close. So we were 173 kilometers above the surface on the third flyby. And I'll actually talk you through the data that we got and the reasoning that we sort of made as to how we came to the conclusion that we did. So looking at this again, I think I've said everything I wanted to hear. I've already mentioned the fact that the particles in all of the rings are mainly water ice, and that the largest ring in the solar system is the E-ring, which is this very diffuse ring, which you saw very nicely in that first image of the Saturn system. So you're going to have to bear with me. Only magnetometer people get excited about magnetometer data. That's why I've got some of my students and postdocs in the room so that they can get excited with me. But as I mentioned a little bit earlier on, the way that you measure the magnetic field is you measure the three components of the field. And so that's what you're seeing there. The top three panels are the three components of the field. The bottom panel is the magnitude or the strength of the field, and that's 24 hours worth of data. One of the things I want to point out is the third panel, you can see a wave in the data, which is actually very close to the planetary rotation rate. And so when we first saw that in the data, we were really excited about what we were seeing because we thought it would allow us to measure the rotation rate of Saturn. But if you look really closely at it, what we realized is throughout the mission, depending on whether you were looking at data coming from the northern hemisphere of Saturn or from the southern hemisphere of Saturn, or whether you were looking at the summer season or the winter season, the period of that wave changed very slightly over time. And so it clearly seemed to be saying it wasn't coming from the interior of the planet. You wouldn't expect those changes to take place on that kind of timescale and be different in the northern and southern regions. And so it's implying it's coming from the atmosphere, and we're still trying to get our head around what's going on. But what I wanted to point out to you was that blip in the data, the jump. So that there. You can see it in the top. You can see it in the top panel and in the middle panel. Those of you with good eyesight or young eyes can see there's a little pimple on the data in the second panel as well. And that was Enceladus. That was our flyby past Enceladus. It's difficult, though, to understand what's going on because the field is so strong, because we were quite close to Saturn. And so what we did in the next slide I'll show you, we subtracted the magnetic field of Saturn away from the data. So what we were looking at was just the magnetic field due to Enceladus. But before I do that, I just want to point out to you how noisy the data is on either side of Enceladus. You can see it becomes very noisy here, and it continues to be noisy further on. And that noise in the data actually gives us an understanding of the fact that there was an injection of water group ions, and those water group ions cause the magnetic field to jitter. But we were actually able to work out that as we got close to Enceladus, there was this sudden injection of water group ions that seemed to be coming from somewhere, and we weren't quite sure. So what we did is we subtracted the magnetic field of Saturn away from the data, and what we're doing now is we're looking down on the north pole of Enceladus. We have the magnetic field and the plasma from Saturn coming in from your left. We've got Saturn off to the top of the page. And the trajectory or the movement of the spacecraft is shown as that line there. So the spacecraft came up from below and traveled off like that. And those little arrows, those little vectors that you see, are the magnetic field that was left in our data due to the moon itself. And one of the really striking things about putting it into that view is it almost looks as though Enceladus is a bigger obstacle than its physical size. It's almost as if there's something that's stopping the magnetic field lines of Saturn from penetrating down onto the surface. So there's something there, and we weren't quite sure what it was to start with. So there was this draping of the magnetic field lines of Saturn around Enceladus, and there was this large increase in ion cyclotron wave activity, which was driven by an increase in water group ions. And we saw this on the first flyby. We were a little worried because we weren't sure that the spacecraft trajectory had been given to us in the kind of resolution that we needed, because it takes a little bit of time to update the trajectory of the spacecraft, where it's pointing and where it's moving. Because as we flew past Enceladus, this was the first time Cassini did that, the spacecraft was moving really quickly, so we could keep Enceladus in its view and take pictures as we flew past. So we actually waited until the second flyby, which took place a month later, until we felt brave enough to start talking about what we thought we were seeing. And so this is what we thought we were seeing. So here we are, looking down. Your eye is looking down on the north pole of Saturn. And so Saturn is the yellow ball in the middle, on the left there. The rings of Saturn are shown around it, and those blue lines are the magnetic field lines of Saturn as they're orbiting around with Saturn. And the little orange ball is Enceladus as it orbits around Saturn. And so if Enceladus was a dead body, the magnetic field lines wouldn't see it at all, and they'd move straight through it, just like we're seeing here. But if Enceladus wasn't a dead body, if there was something that was stopping the magnetic field lines of Saturn from moving through the moon, then you would see something like this. So now our eye is moved to looking sideways on, and here we're looking at Enceladus itself. The blue lines of Saturn are moving towards it, and they can't penetrate down onto the surface. Something's stopping them from getting down onto the surface. And one way in which you can do that is you can have an atmosphere, just like we have on the Earth. The upper regions of the atmosphere become ionized by the effects of solar radiation, and that ionized region stops the magnetic field lines being able to penetrate down. We have something very similar that happens at Titan, the large moon of Saturn. And so those black lines there are the field lines of Saturn, and they drape around Titan because they can't penetrate through the upper regions of the atmosphere. And so I went out to the Jet Propulsion Lab and I gave a presentation to the Cassini project and to the Cassini scientists, and I said that based on the first two flybys, we thought we were seeing a diffuse atmosphere all the way around Enceladus because our magnetic field data was telling us that the field lines of Saturn couldn't reach the surface of Enceladus. They were draping around it. And I also told them that we were seeing this large increase in wave activity, which we think was as a result of injection of water group ions. Now, before I gave the science presentation, I was standing in a coffee line, and the person responsible for essentially driving the spacecraft was standing in the line in front of me. And he turned around and he said, "Hi, Michelle, what are you doing? I didn't think we had a Cassini project meeting." And I said, No, I've come out, and I told him what we saw. And he rubbed his hands together in glee, and he said, "Oh, that's cool. I've always wanted to fly closer to a planetary body than anyone else." And I thought, okay. I went into the science meeting slightly more confident that I had at least one person on site. So we had lots of discussion about this. You know, the fact that we had always been interested in Enceladus, we thought it might be the source of the E-ring, but we weren't quite sure how it could be. Persuaded people that we should do it, but also it meant that by changing the trajectory of the spacecraft, we would have to use some extra fuel. That might impact the kind of observations we would make later on. But also it would change the science that some of the other instruments could do, because on the Cassini spacecraft, we had 11 different instruments. They all wanted to point at different places at the same time. And so we actually spent the 6.5 years it took us to get out to Saturn planning in fine detail the first 4 years' worth of observations that we were going to make. And so what we wanted to do was turn it all on its head and do something different. But the agreement was made that this change would happen. And so 4 months later, the third flyby took place. I didn't sleep for about 3 nights beforehand, because if we had seen nothing at all, no one would ever have believed anything I said again. But luckily, we saw some really interesting stuff. And this is, I won't show you the data. I won't put you through another plot of the data, but I will show you the schematic that we put together based on this third flyby. And that's what we found. Instead of the atmosphere covering the entire surface, it was focused just at the South Pole. It was almost like a cometary plume of water vapor coming off from a comet as it got close to the sun. Interesting thing, though, is that if it had only been focused at the South Pole like that on that first flyby that we had, I don't think we should have seen the data that we did see, because the first flyby actually took place way above the North Pole of Enceladus. And so even now, I'm surprised that we actually saw the signatures in the data that we did. We think the activity that I'm going to talk about changes over time, so that might be the reason. But because we went so close, all the other instruments were able to take really great data as well. And so I'm going to show you data from some of those. So this view that you see here in the top left, we have a view of Enceladus taken by the imaging camera on board Cassini. And what you will notice is that at the South Pole, there are these fractures at the pole, those blue lines that you can see, which the imaging team called tiger stripes. In the bottom left, you can see data from an instrument that was able to remotely sense the temperature of the surface. And the view on the left shows you what they expected to find. They expected to see that the hottest temperature of Enceladus was at the equator because that's where the solar rays are strongest. And what you can see on the left-hand side again, but on the second image there, is that yes, it was warm at the equator, but there was a hot spot that we saw at the South Pole. Now, when I'm talking about hot spots, this is all relative. We're out at Saturn, it's about minus 150 degrees Celsius, but if it's 25 degrees or 30 degrees warmer than it should be, then that's construed as a hot spot. So what we did is we overlaid the temperature data on top of the image, and you can see that the hottest region, which was at a balmy minus 170 degrees or minus 100 degrees Celsius, was lying right over one of the cracks. And so the implication is that these cracks went right down into the interior, and internal heat was leaking out of these cracks on the surface. Now, this was a real surprise because, as I mentioned a little earlier on, Enceladus is pretty small. It's about 500 kilometers in diameter. And so we thought it would have long since cooled down from when it first formed. And so the fact that there is still internal heat leaking out of Enceladus is a real surprise. There was lots of other data that was taken as well. This shows you data that was taken by the imaging spectrometer on board Cassini, where what they did is they used data from the 3 Enceladus flybys to essentially derive a compositional map of Enceladus. And the top left shows you the image that was taken by the visual camera, just to be able to give you a reference. The 2.2 micron region, that's in a different wavelength, that actually shows you how reflective the surface of Enceladus is. Bottom left shows you the ice absorption, and the image in the middle shows you the organic material. That's the absorption of organic material. And so if you put all of those different wavelengths together, what it's essentially showing you is those red regions which are lying along the cracks or the tiger stripes have got a huge amount of organic material lying on top of them. And so you've got heat leaking out, you've got water vapor coming out, and you've got organic material coming out as well. This here again is from the VIMS instrument, the same instrument as the previous slide, and this was on a slightly later flyby. This took place in November of 2005. And what they did there is they actually looked at the composition of the plume. They looked at the composition of the E-ring itself and the composition of the surface. And what they found is that the shape of the spectra from the surface from the plume and from the E-ring was exactly the same. So the implication is that the E-ring was the source, or the E-ring was being built up by material coming from the plume. And so this essentially pinpointed the fact that, as people had thought for quite a long time, Enceladus was in fact the source of the E-ring, and we had now found how it could be the source. And this image here shows you a view from the camera again on a rather a distant flyby when the spacecraft turned and looked back at Saturn. And you can clearly see how dense the plume is. The different colors are showing you the different densities of the plume. And you can see there are different sources on the surface. I'll show you that in a view in a few slides. But it essentially towers above the south pole of the moon itself. And the amount of activity seems to change over time. We think it's linked to where Enceladus is in its orbit around Saturn. In some parts of its orbit, it's slightly closer to Saturn than on other parts, and so the gravitational pull of Saturn is stronger, and so that means the tidal forces are different. And so we think the cracks are opening and closing in different places depending upon where they are in orbit. And so this was actually a schematic that was put together based around about the time of lots of papers that were written after the discovery of this plume, which essentially almost shows Enceladus as the powerhouse of the magnetosphere of Saturn. All this material emanating from the south pole of the moon, which is essentially going towards forming the diffuse E-ring that you saw in the first image that I showed you. So this here looks at a close-up view of the North Pole. And it shows you the tiger stripes, and it actually also shows you the different temperatures of the tiger stripes. And I've got a little bar along the bottom that shows you how big 50 kilometers is. And so it gives you an idea of the extent of these tiger stripes. And the little yellow stars that you can see there, those are individual sites where the water vapor and organic material is leaking out. And as I mentioned, these different sources are opening and closing over time as Enceladus moves in its orbit. And that's one of the reasons why we think the activity increases on occasion and it decreases on other occasions. This here shows you data that was taken by the ion neutral mass spectrometer on Cassini. Now, this is an instrument that was able to almost taste the environment it was flying through. And so as we flew through the plume, INMS would actually measure what material was in the plume. And so you can see there that we have water vapor, which we knew based on the magnetometer observations. You've also got methane, you've got simple and complex organic material, and you've got carbon monoxide and carbon dioxide as well. And so scientists got really excited when we were really sure that there was organic material. We knew there was some on the surface, but we now knew there was some coming out of the plume as well, because one of the reasons why scientists like to go to other planets is you're always quite keen to see where the life might be able to form somewhere else. And so you need 4 things for life to be able to form. You need a heat source, which we have at Enceladus. You need there to be liquid water, which we know that we have. We know there's a liquid water reservoir under the surface, which under pressure is coming out of in the plume as water vapor. You need organic material, which has been confirmed that we have at Enceladus. The 4th thing that you need is you need those first 3 to be stable over a long enough period of time that something can actually happen. And that's what we're not sure of at Enceladus. We're not quite sure how long we've had this environment there. And so based on the potential for life to be able to form in an environment like this, there was a real focus by the Cassini mission in its various extensions that we had to have a much closer look at Enceladus. So we flew below the South Pole on numerous occasions, and just before the end of the mission, we actually had a flyover of the North Pole. And although we haven't seen any activity at the North Pole, what we did see is what looked like old cracks on the surface, old tiger stripes. And so maybe back in the distant past, there was some activity that was taking place at the North Pole. But in the time that Cassini was there, it was all focused on the South Pole. One of the things that isn't shown in this image but was found on a later flyby was ammonia was found in the plume. And that helps us get an understanding about why we might be able to have liquid water out at these great distances from the sun. Because if you have ammonia, it almost acts as an antifreeze, and that might be why we're able to, one of the reasons why we may be able to have the water being liquid out at those great distances. Now, I think the last slide, I've got 2 more slides on Enceladus. This slide here shows you a close-up view of one of the tiger stripes. The different colors show you pockets of heat along the fractures. This is actually a 40-kilometer segment of a tiger stripe called Baghdad sulcus. Don't know where they come up with the names, but the imaging team always calls them lots of names. Now, this is the highest resolution image that we have, where we've also got the temperature map as well. And so you can clearly see that there is heat coming out of these cracks, and it's at about a minus 100 degrees Celsius. But if you have a close look, most of the heat seems to be actually coming from the flanks of these cracks. You've got V-shaped valleys, which are about 500 meters in depth. And the slopes seem to be covered with some smooth material. So almost as though, the water vapor plume is coming out and some of the material is falling back. And so it makes the insides of the cracks smooth. And the last slide I wanted to show you linked to Enceladus was an artist's impression of what Saturn might look like from the surface of Enceladus. But based on the observations which Cassini made at Enceladus and the discoveries that we made about the liquid water ocean, the heat source, the organic material, there's now a real focus on trying to go back to Enceladus to better understand what was going on. But from my perspective, I think one of the best outcomes of the Enceladus work is the fact that all the teams work together To be able to understand an environment so far away, you need to put all the different data sets together. One instrument team can't do it on their own. And I think this is when the Cassini project really came together as a team. We had to put our data together to best understand the observations that were going on. One last point about Enceladus is it's very difficult to go into orbit at Enceladus. Because it's so small, its gravitational field is very small, you need a huge amount of fuel to be able to get yourself into orbit. And that's going to be one of the problems at actually orbiting around the moon. But that's a problem for younger scientists. Okay, so in the last 20 minutes or so, what I want to do is focus on the Cassini end of mission. This occurred last year on the 15th of September. And this shows you a view of the last 6 months or so of the mission. So we have Saturn right in the middle. We have the orbit of Titan that you can see out at 20 planetary radii away from Saturn. And the reason that that's shown there is partly to give you a context of the size, but also Titan was used as a gravity assist. We used Titan to get us up out of the equatorial plane so we could fly over the poles. And there were two different phases to this end of mission. The first one was called the F-ring phase, or the ring grazing orbits, and that's the gray orbits that you can see there. And there, the closest approach to Saturn was just beyond the edge of the visible rings, so just beyond the edge of the F-rings. And there were some glorious images taken of the rings during this period. From my perspective, what my team did is we used the data that we measured on these orbits to best understand the kind of observations we were going to see when we got really close in. And then the last 6 months of the tour, April to September, well, it's not quite 6 months, but those are the blue orbits that you can see there. Those were called the grand finale orbits. And there what happened is the closest approach took place just above the atmosphere of Saturn. So we essentially dived between the gap and the rings. I say that as if we weren't worried about it at all. I'll talk about that in a couple of slides' time. And then the orange orbit is the final orbit. That was the impacting orbit. That was the orbit that took us into the atmosphere of Saturn. Now, the reason we did this is that the spacecraft was running out of fuel. We knew we couldn't go on forever. We could have put ourselves into an orbit where we didn't need to use fuel and we would just orbit around Saturn. But eventually, over time, we would have lost control of the spacecraft. And we wanted to make sure that the spacecraft did not crash onto the surface of Enceladus or crash onto the surface of Titan, because those are both moons where they have the potential for life to form. You don't want to crash a man-made object on the surface of a moon that might have life on it. People say to me, what about the Huygens probe? Well, the Huygens probe was put through a very careful cleaning process known as planetary protection. And the probe was cleaned and really carefully before launch so that it wouldn't take any man-made object or any microbes down onto the surface. So we knew we had to do something to kill the spacecraft, but we wanted to go out in as spectacular a fashion as possible. And the way to do that, burning up in the atmosphere is pretty spectacular, but we wanted to get great science as we did that. And the real outstanding question about Saturn is what's going on inside. We don't understand how the internal planetary field is generated because, as I mentioned at the start, there isn't a tilt between the rotation axis and the dipole axis. And planetary dynamo theory tells you you need a tilt. If you don't have a tilt, you shouldn't be able to generate the field. At Saturn, we haven't been able to find a tilt. So we thought if we got inside of the rings, we would be able to measure that tilt. And also the gravity data is really important close in for us to be able to understand the internal structure. So it was gravity and magnetometer measurements that were really driving the design of the end of mission. No pressure on us at all. The other thing that was important, and let me mention it just before I forget, is I mentioned right at the start that for us to calibrate our instrument, we needed to roll the spacecraft. One of the things about the really close-in orbits was that we were in a measuring range of the instrument that we hadn't been in since 1998 when we flew past the Earth. So we didn't know where the zero level of that range was. And so what we did is, I must be quite persuasive, because I persuaded the Cassini project to roll us around closest approach on 4 separate orbits so that we could actually calibrate the data. And it's taken us a long time to calibrate it, but it's really beautiful data. You don't quite understand it all yet, but it's beautiful data. So this just shows you a zoomed-in version of us skimming the cloud tops. Shows you how close we got. We were about 2,000 kilometers above the cloud tops to start with, and we slowly got closer and closer. And what we were wanting to do is, by measuring the magnetic field lines outside of Saturn, it allows us to hopefully work out what's going on inside. I mentioned that we assume the magnetic field is generated by planetary dynamo action. You've got this overturning, bubbling motion taking place, and you've got the convection and the rotation taking place. But that tells you should have a tilt between the two axes, and we haven't been able to find it. But by getting an understanding of the interior, it almost allows you to see inside the planet, to get an understanding about what's going on inside. We think there's possibly a small rocky core. We think the Dynamo region is a fluid metallic region. You need it to be a conductive region because you need currents to flow. You won't generate the field unless you've got currents flowing. And so we think it's happening in a fluid metallic hydrogen region. And then there's probably a region above that as well. But by the time we understand our data and the gravity data, we will hopefully have a better view of what we think is going on inside. So let me move on to the end of mission scenario now. So this was an artist impression of the spacecraft making the first dive between the rings and the surface and the atmosphere of Saturn. And the plan was that there were 22 of these really close in orbit. We were really concerned about what we were going to find in that gap. It looks like a gap, but we weren't quite sure if there'd be energetic dust in the gap, which might damage the spacecraft and the instruments. In fact, at Saturn orbit insertion, when we first arrived at Saturn back in July 2004, there was an energetic dust particle which hit the high-gain antenna. And so there was a hole in the high-gain antenna ever after that. And so what we did is we flew in to the gap with the high-gain antenna pointing in the direction of travel, so that if there was anything there, it would damage the high-gain antenna, but not damage the spacecraft or the instruments behind the high-gain antenna. That was all very well for the instruments protected by the high-gain antenna. We were on a boom. And it wasn't helped by the fact that I went out to the Jet Propulsion Lab in time for this first close flyby, and the project manager came up to me and said, "We're really worried, you know." And I said, "Oh, no, but the high-gain antenna." He said, "No, we're not worried about us, we're worried about you." And I said, "Oh, thank you very much." So it was a bit nail-biting, but we survived that first orbit, and in fact, we survived all 22. And that was spectacular. You know, the spacecraft was not designed to do this. The spacecraft was originally designed to last in orbit around Saturn for 4 years. And 13 years later, we were still going strong, and we're doing things with the spacecraft that we would never have even contemplated doing when we first got there. And one of the reasons we were able to do this is it was fascinating to watch the spacecraft team, because when we were first launched and also when we first got to Saturn, they were very careful of the spacecraft. It's almost like learning to drive a new car. Each car has its own nuances, and you have to learn what you can do and how far you can push it. But by the time we got to the end of the mission, they could do almost anything with it. The only thing they couldn't do was find extra fuel. By the time we got to the end of the mission, we were on fumes. We really were on fumes. In fact, the spacecraft team was concerned that we weren't going to make it to the end of the mission, because the error of our knowledge of how much fuel there was left, you're never quite sure how spot on you are. But we were on the last few fumes by the time we got right to the end. Okay, so we had 22 of these orbits. We're still working really hard on the data. We still don't know how long a day on Saturn is, but we will find out. Every time someone asks me when we're going to know, I say a few months. I hope there's no dates around when I say that, but we are working the data really hard, and there is a lot more to learn from the data. But let's just finish with a few of the images. This here shows you the resting place of Cassini. This was an image that was taken in the infrared by the VIMS instrument, actually the day before the end of mission. And we were able to work out after the end from the spacecraft trajectory where the spacecraft actually went into the atmosphere. But this instrument actually allowed you to get a sense of the heat coming from the interior of Saturn, and the clouds in the atmosphere are effectively silhouetted against the glow of the heat coming from the interior. And just to give you an understanding about where it is in context, this actually occurred just above the equatorial region in the northern hemisphere. And so every time I see the slide, the hair on my arm still stands on end. This is a view in the Mission Control Center after the end of mission, where they realized it was over. I think for me, maybe the most poignant moment was we were all out at Jet Propulsion Lab watching the data, and the way in which we knew that the spacecraft was talking to the Earth is there was a line, a peak of data, and that was the spacecraft sending data down to the Earth. When that peak went away, it had stopped talking to the Earth. And the peak disappeared, and our hearts sank, and then it came back again briefly. And in fact, it turns out that it was a side lobe from one of the stations that we were seeing. But my perspective of it was that it was a spacecraft hadn't been told that it was going to burn up in the atmosphere. And so it was the spacecraft reorienting itself, saying, I'm still here, we're still going to send data down. So we're going to end by showing a short movie that NASA put together. Now, in fact, this movie was put together 6 months before the end of mission, which described what the spacecraft was going to do. Most of us didn't think it was going to survive to the end, but it survived to the last second. And in fact, the mag data was one of the last data points that we got. But you'll see essentially an overview of the mission and then what happened at the end. So I hope the sound isn't too loud, but let's move on to here we go.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
4, 3, 2, 1, and liftoff of the Cassini spacecraft on a billion-mile trek to Saturn. We have cleared the tower. Which program is in? This program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
To the SOI burn attitude or pointing position, and light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system. For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
Thank you very much.